All right, hello team, and welcome back to Unit 4. Today we're going to be going through the Day 2 notes, which is just going back to related rates, the things that we did last time, and we're just going to talk about a couple of special types of examples that happen with related rates, some specific instances of a related rates problem. And how to attack those problems and what makes them a little bit different from the ones that we did last class. So last class we introduced what is a related rate. Well, it's just a relationship of rates in a situation where things are dependent on time. So it's moving situations where we have things that are changing and we are finding an equation of rates, and then we plug in to find rates that we want. Okay, so today we're going to be focusing on related rates examples that deal with cones and cylinders. So cones and cylinders have special properties that make them different than some of the other situations. I know we've done a lot of right triangles and angles and rectangles and circles, but cylinders and cones, and specifically dealing with the volume of those, are going to be kind of a little bit different. So just to kind of recap, if you remember from like 7th grade, the volume of a cylinder is just the area of the base. So it's pi, let's see, pi r squared h. Oh, that's too thick. There we go. Let's try this one. And the volume of a cone is just pi r squared h and a third of that. So a cylinder is just the area of the circle times the length or the height of the cylinder. Okay, the volume of a cone is the length of the volume of a cylinder divided by 3. A lot of times you're going to see that one written as pi over 3. They'll take the 1/3 in the pi and they'll put it together to be one kind of constant. That's the way that I tend to write it, so I will probably write it this way, but 1/3 pi and pi over 3 are the same thing, okay? So we're going to be using these two formulas today. This one will always be provided to you, volume of a cone and volume of a sphere, okay, of a sphere, which is 4/3 pi r cubed. Okay, those two will be given, but volume of a cylinder you should know. All right, so we're going to jump right into a couple of examples and talk about there's like two ways of doing this when you have a cone or a cylinder problem. There is a little bit of a given information that's implicit in these situations that you're going to need to use. So let's go through and I'm going to show you what that like given information, implicit given information is, and then how we would use that to solve the problem two different ways. So I'm going to be doing this first example two different ways to kind of show you the difference between solving them. Oh my gosh, a tank of water, guys. We haven't seen a tank of water ever before. A tank of the water in the shape of a cone is leaking water at a constant rate of 2 feet cubed per hour. Okay, so if I'm writing down these numbers right away to kind of figure out what I'm given 2 feet cubed per hour. That is a volume rate. So I know dV dt is 2, and since it's leaking out, I'm going to say -2. Okay, so I could label that here, dV dt equals -2. Okay, the base radius of the tank is 5 feet. So the tank itself is 5 feet. That's not changing. And the height of the tank is 12 feet. I'm going to go ahead and label those on my diagram because they are not changing. The tank isn't changing size. It's the water inside the tank that is. At what rate is the depth of the water in the tank changing? When the depth of the water is 6. So I'm trying to find the depth of the water. So let's figure out the depth of the water is changing. I'm going to call it height for depth because I don't want to write dd. So I'm trying to find the rate of the height of the water when the depth of the water is 6. Notice that when I labeled the water, I did not label it with 6. As it's not always 6. It's only 6 at an instant. So when I freeze my moment and draw it, then I can put 6 in my moment. The other thing is that this water is going to have a radius, but that radius is changing. Now, if I think about it, it's leaking out. I'm going to have a negative dH dt, and the radius would be shrinking. That's going to make a negative dr dt. Okay, so now that I kind of have all the information that they want to give me, I need to start with an equation that relates these variables together. So I have a rate for V. So I'm going to have volume, radius, and height. I'm going to start with the volume of a cone. Now I'm going to split my paper into two and talk about the two ways. Either way, I'm starting with the volume of a cone. Okay. Now, the trick to a cone, not a trick, but part of the given information, okay, is the fact that if I look at this picture, there is a relationship between the radius and height of the water and the radius and the height of a tank. They make similar triangles. Part of the given information here that they're always going to be looking for is the fact that the radius and height are always going to remain the same proportion. So the radius to height is always going to be 5 to 12. Okay, so this is given implicit given information based off the scenario. Based on the fact that this is a cone, I know this proportion has to exist. Now I'm going to use this proportion to help me in one of two ways. I can either take my original equation, and in this way I'm going to eliminate a variable. Now you're like, Ms. Bowman, what the heck? How can we eliminate a variable? I have three variables in this expression, v, r, and h. Now, if I think about it, who I'm trying to find is the rate of height. I want the rate of this height. Who I have already is the rate of the volume. Okay, so I have the rate of the volume. I want the rate of the height. Notice that there's one variable that I do not have the rate of and I do not want the rate of, and that is the radius. So what we can do here is we can replace the radius using this proportion. So here's how I would do this. I'm going to move this down and I'm going to say, okay, if my radius to height ratio is always 5 to 12, what that tells me is that my radius is always 5/12 my height. I can use this relationship as a substitution in this problem. So I'm going to rewrite my equation to be v equals pi over 3. And instead of r, I'm going to write 5/12 h squared h. Now, look, we have an equation that relates just volume and height together, which is kind of what I want. I have less variables, and I can actually like clean this function up because it's just squaring. I'm going to go ahead and square that to make that 25 over 144 h squared times h. And look, guys, I could simplify that further. Volume equals 25 pi over, I want to do that right now, 3 times 144 h cubed. So now look at the rewrite of my function. Now I have a function for volume in terms of just height, and I've gotten rid of all the multiplication and all the r's, and I have a nasty constant, but on the flip side, a really nice function to implicitly differentiate. And so what I would do from here is now I'm going to take the derivative with respect to time. I'm going to leave this 25 pi. I never multiply this 3 times whatever on the bottom. I'm going to show you why. Because I know when I take the derivative h cubed, it's 3h squared times dh dt. Don't forget the chain rule here. H is a function. And I see those 3's are going to cancel. So now I can find dh dt at my moment. So my moment in this cone is that the height of this is 6, and I know the rate of volume is negative, what was it, -2. So I'm going to say -2 equals 25 pi over 144 times 6, because that's the height, squared dh dt. And then if I isolate dh dt, I get dh dt is equal to -2 over 25 pi over 144 times 36. Now I can do a lot of simplifying, or I could just tack on my units. So the height was measured in feet and my time was hours. So my height, it would be feet per hour. That's a number, guys. I don't have to clean this up. Now, if you just need me to clean this up for the sake of practicing, because you're like, Miss Bowman, I need you to clean it up. Okay, so let's clean it up. So -2, 36, 12 goes into 144 12 times and 3 times, and that actually is 1 and 4. So it's -2 over 25 pi over 4, which is the same thing as -2 times 4 over 25 pi, and that gives me -8 over 25 pi feet per hour. And that would be like the simplified, cleaned up numerical answer. Okay, so that's option 1. Now, option 2, you're still going to use that proportion, but we're just going to take the derivative like we see it here. Now, do be careful here because in this second version, I do have two variables being multiplied together. And so when I take the derivative here, I'm going to have to use product rule. So if I start this problem out, I'm going to have dv dt equals, now pi over 3 is just a constant. It's going to come down. And now I'm going to use a derivative, udv plus v du. R squared times dh dt plus h times 2r dr dt. And that would be my derivative. Now, dh dt is who I want, and I always put a box around who I'm looking for, because now I need to look at this problem and make sure I have all the information that I need. I know at this moment that the height is 6. So if I freeze frame my thing, again, I only know the height. I do not know the radius, and I don't know the rate of the radius. But I can use the fact that r over h is equal to 5 over 12 to help me find this information. So here's my little aside. Okay, so I know r is equal to 5/12 h. So r would be equal to 5/12 times 6, which would just give me 5/2. Okay, so now I have my r. If r is equal to 5/12 h, then I know dr dt, guys, is equal to 5/12 times dh dt. If I take the derivative of that relationship, kind of like what we did with our particle last class, then we would have this. So I would just get 5/12 dh dt is equal to dr dt. So now what I would do is I'd plug all that information in. And I'm going to do it down here because I just did not leave myself enough room. So dv dt is -2. I have pi over 3. And then I have r, which is 5 over 2 squared times dh dt, which is what I'm looking for, plus h, which is 6, times 2r, which is 5/2, and then dr dt is 5/12 dh dt. And now I'm going to start cleaning this up. So -2 equals pi over 3. That gives me 25/4 dh dt plus this one. I'm going to get 25. Let's see, these 2's would cancel, and that would leave me with 25 over 2 dh dt. I do have like terms here, so I'm going to add those like terms together. -2 equals pi over 3 times, let's see, 50/75 over 4 dh dt. Now, if I simplify that a little bit more, I get -2 equals 25 pi over 4 dh dt. And then I would divide both sides by that, and I get -2 times the reciprocal, because I don't divide by fractions, dh dt. And look, guys, if I do it this way, I still get -8 over 25 pi feet per hour. So either way I do it, I end up getting the same result. In the first method, I used the proportion to eliminate a function before I took the derivative, and then I solved it. In the second version, I took the derivative first and then used the proportion to find my radius and my rate of my radius depending on what I wanted. So no matter how you do it, okay, you're going to use the proportion either to eliminate a variable or to replace a rate. So either one we're going to do. You guys kind of pick, practice, see what you like. Now I could do the same problem again for r instead of h. We would have just said, instead of r equals 5/12 h, we would have said h equals 12/5 r and like use that as the substitution. Okay, so let's try one more. I have no idea what happened to the picture here, but I'll fix it. Find the rate of change of the volume of a cylinder. Okay, so I have a cylinder here. Let me draw a picture. That's probably what that was. Find the rate of change of the volume. Okay, so I'm trying to find dV dt when its radius is 6 feet. If its height is always 3/2 times its radius, and the radius is increasing at a rate of 2. So I have a radius here that's increasing, and then I have a height here. And they already give me the proportion. So we didn't even have to set up a proportion in this one. They gave it to us. So I'm going to start with the volume of a cylinder, pi r squared h. And now I'm going to figure out who I'm trying to find. I'm trying to find dV dt when r is 6, and they give me dr dt. Notice that I do not have dH dt, and I do not want dH dt. So my option number 1 for this problem, okay, is to take the fact that h equals 3/2 of r and plug that, ooh, that's an r, into that equation. So v equals pi r squared times 3/2 r. Now this one's a little nicer to clean up because this h is just h as opposed to squaring it like we did in the last example. So if I were to clean this up, I'm just going to multiply 3 and pi over 2, and then I have r squared times r, which is r cubed, and that would be my function. And now I'm ready to take the derivative. dV dt equals 3 pi over 2 times 3r squared dr dt. And lucky for us, like we already know at this moment what our rate of the radius is. It tells us that the rate of the radius is 2, and it wants it when the radius is 6. So I actually have all the information. I don't have to do any side work, which is rare. Okay, but now I'm going to plug in my radius, which is 6, and my rate of my radius, which is a constant 2. And if you notice here, like dV dt is already isolated, so all I have to do is like simplify this right-hand side. So the 2's would cancel. That's going to give me 36 times 9, which is 36 times 9, 324, I believe. 324 pi. And now I just need to figure out my units. Volume is measured in cubic units. So we have feet and minutes, so feet cubed per minute. And that would be option number 1. It's the option I prefer. But again, if we do it the other way, let's see, we'll change the color back to green. If I wanted to do it the other way, I just have to, 1, pay attention to the fact that this is a product rule. So dV dt is going to be equal to pi and then r squared times dH dt plus h times 2r dr dt. Don't forget the little chain rule with the r. Now, I know my r is 6. So I can plug in 6. And I know dr dt is 2. But I'm missing h and dH dt. But I do have this proportion. So if r, at this moment, if r is 6, then 3/2 of 6 is going to be 9. So I know my height is 9. To get the rate of the height, I would take my proportion and take the derivative. So if h is equal to 3/2 r, then dH dt is equal to 3/2 dr dt. So I'm just going to put 3/2 dr dt in here, and since dr dt is 2, it would just be 3/2 times 2. And now if I simplify this, I end up getting pi, and then 6 squared is 36, and we got 36 times 3, which is 18,108, plus, and then here I have 6 times 2 is 12, times 2 is 24, 24 times 9 is 6, 3, 216. And if I add that together, I get 324 pi. feet cubed per minute. So again, do I get the same thing both ways? Yes. Pick the way that is comfortable to you. And that is related rates.